And ladies and gentlemen, coming up is the presentation by Shri M.S. Shantha Kumar, Technology Manager Hitachi ABB Power Grids. Working on HVDC and STATCOM technology, innovative solutions for HVDC transportation, STATCOM and load balance SFC solutions for critical applications like railways, transmission and distribution utilities and other industries. He developed and implemented cutting edge technology solutions for India market requirements, several first time critical projects and solutions for key customers like Reliance, ONGC, JSW, Tata, etc. Published papers on HVDC and converter technologies in SIGRE and other conferences. And over to you, sir, for your presentation.
Okay, good afternoon. Yeah, this is Shantha Kumar from Hitachi ABB, and today I will have first of all, good afternoon, good morning, and greetings to everyone whosoever is participating. And today I have been asked to give brief introduction and then maybe call it as a presentation on the railway quality issues, and then how we can address through the new latest technologies, whatever we have like STATCOM, railway road balancer, and then SFC. So I will, due to the time limitations, I will straight away go to the presentation. And you can see from this slide that we have a generation on one side, consumers on other side, and in between we have a transmission to carry the power from generation to the consumers. And left side you can see the latest introduction over the period of time is basically the renewables. And then even in the Indian railways and other part of the metros, we are now seriously working, our government is seriously pushing for integration of renewable energy into the railway and metro networks, where it can be called as a green corridor or green train, green metro. So we can give any name, but what is very important to understand here is that more and more renewables will get added into the network, and then we will have more and more quality issues related to the infrastructure. What we have may not be catering to the required load demand, or intermittency of the renewables may not be able to satisfy through these existing networks. So we need to augment those both the network related or the transmission related infrastructure. At the same time, we need to also address the quality issues what we have in order to enable the railway or the metro to work more and more faster, and then we will have a more and more stronger transportation system. So we whether it is ABB or Hitachi ABB or XYZ, we will have solutions to address these quality power quality issues. If we talk about shunt compensation, we have SVC, that is a very old but very robust technology. Static var compensator we call it as, and then we have STATCOMs, we have hybrid solutions with combination of both STATCOM, SVC, and maybe fixed capacitor or inductor elements. We also have as a solution available now as a synchronous condenser compensation as a tandem working control. We can have both STATCOM, synchronous condenser, maybe some fixed capacitors working towards satisfying the requirement in terms of the reactive power compensation or the inertia requirements to strengthen the network what we have in the event of renewable energy integration. This is very, very important. So what are the benefits we get by doing so? It is not that just we want to put as a STATCOM or some hybrid solution, we just add on to the network. We will have to understand and appreciate the benefits, real benefits, what railway network is going to get. That is basically increasing the reliability of the overall power supply system, improving the overall productivity of the railway network, and then integrating more and more renewable energy, because the renewable energy requires definitely the adaptability of the overall network to adjust to the new situation, unlike what we had in a fossil fuel kind of power plants where irrespective of the network and consumers status, almost we had a very reliable power feeding to this consumer base. So I will not get into the various combinations of solutions we have. So just see from the right hand side, we have a specific products for railway frequency converters, and then we also have what is called as a load balancer, and then we can also use the existing products in terms of the shunt compensation like SVCR, STATCOM, in tandem with these products like SFC, load balancer, so that the overall solution can be provided to address the quality issues what we have with the railway or metro network. So before getting into the real-time solutions what we can provide, you can just see from the overall aspects of the railway network what we have. So there is a great change in terms of the overall network what we are seeing, which we have also discussed. So in this case, what we need to also consider as an important factor is that what is the grid code where you are located, and then what are the parameters we need to address, like what we have unbalanced voltage fluctuations, harmonics, and then the power factor requirements. These parameters, mitigating these issues with respect to the grid code, not only make your overall network more efficient, it will also enable more and more renewable energy integration without really affecting the network what you are connected and wherever it is located. So in terms of the solutions, we can see these what is demonstrated here. So it is all across the world is the overall scenario we have considered, and we have indicated what all the best possible solutions at what stage. So we can have a normal substation drawing the power from the network and then feeding into the railway catenary network. And we can have a static frequency converter as a solution where it will take the three-phase power in and convert it to single phase and then feed into the railway network, railway catenary. And we can also have in between a load balancer. I will explain what is load balancer in the next slides. And this will basically compensate for the overall unbalance in the load, because when we connect two phases out of three phase, naturally you will have current through the two phases, but another phase is unconnected, and then the current is zero related to the real power. So in that sense, we can have the load balancer to balance out the overall negative sequence component generated due to this unbalance, and not only that, it will also compensate for the reactive power and then balance the entire network what we have connected. And the static frequency converter is another product which is extensively used in Europe, Australia and other countries, which will not only can adjust to the any different frequency between the catenary and the supply frequency. Of course, may not be very big criteria in India because the same frequency network is available all across. So what is very important to notice here is that this static frequency converter not only balances the electrical parameters on the three-phase side, it will also enable the balancing of the entire corridor where this catenary network is connected through this particular static frequency converter. So if we look at the load balancer, what we call it as, this is similar to a STATCOM what we have, but it is not just connecting to the network to compensate for the reactive power, it will also compensate for the unbalance in the real power. So when we have two phase connected and the third phase is unconnected, so this load balancer will draw the power from the unconnected phase and then feeding it to the other two phases wherever it is connected, and to the extent of unbalance it will correct it, and so that the network will not feel any unbalanced currents flowing through this as part of the real power feeding into the catenary. At the same time, this will also compensate for the reactive power and balance the the power factor to the whatever the value required. Ideally it is unity, and then also it will mitigate the harmonics and other grid code requirements to make the entire network complying to the not only grid code requirements, but it will also balance the power and then increase the overall network efficiency. So in that sense, with the same infrastructure, you can draw more power from the same, and then you can feed it to the network in the event of the overall traffic increase or the frequency between trains is increasing. So this is just a demonstration what I am showing it here. Before getting into this network, you can see that the size of the load balancer what we need to compensate for both real power unbalance and also the reactive power compensation is that what is the load MVA consumed by the railway network, train harmonics, whether it is lower order or the higher order harmonics we should be aware, and then what is the worst case scenario we expect in terms of both reactive power compensation required, that is power factor compensation, and then what is the unbalance we accept as a worst case. For example, 220 kV it can be 1%, and less than that can be even 2%. And then what are the power quality requirements, and then for example voltage unbalance, power factor requirements, and then what is the evaluation window as per IEC. For example, it is 10 minutes or 1 minute, what is that we need, and then what kind of harmonics levels we are expecting as a grid code requirement, and then grid parameters like what is the short circuit power and what all the background harmonics present in the network. So these are the influencing parameters which will decide which all will decide what is the size of this load balancer. Having decided what is the size of the load balancer, you can see one scenario here that two railway stations or the metro feeding stations are connected to a network that is called as high voltage grid, and then when they are connected and balancing the overall power drawn from this railway going from AB to CA segment, but when one station is down, for example this station feeding to the CA is down, the entire current is drawn from only two phases. Power is fed from the one feeding station, so the unbalanced factor will dramatically change when we have this kind of scenario compared to what we had in the previous where two stations are acting. So because these alternatively two phases are connected to the individual station, so that is where this scenario happens that one side you will have a totally extreme end of the unbalancing, and when they are all working it can be as minimum as possible. So this load balancer understands the scenario in the event of any change in this, and then adjust its feeding and balance the entire network for the both real power and also the reactive power compensation. So that is what is demonstrated here. I will not get into the more technical details. So what we see here is that this load balancer is connected to the three phase, and whereas the railway network feeding station is connected to the two phases. So one phase is unconnected. The load balancer will draw the current from the unconnected phase and then try to feed or compensate for the connected phases. So in that sense, not only the reactive power, it will also compensate for the real power unbalance. At the same time, when we have a static frequency converter feeding to the railway network, say in this case two phases 25 kV and then the neutral, and it is drawing of course the power from all the three phases. So in that way we can control the real power flow from network to the railway feeding catenary, and also it independently compensate for the reactive power not only at the network side, it is also compensating for the railway network. So in this sense, this static frequency converter can compensate the entire railway network, that is single phase railway network for the reactive power, balance the voltage, and not only that, any excess energy due to the regeneration can be fed back to this network. So overall efficiency of the railway network will increase. It will reduce the real power demand to the extent of 20% or more, and not only that, it will improve the overall efficiency of the network by compensating the reactive power and reduction of the losses. Plus it will also take care of the grid code requirements like harmonics and reactive power mitigation at the network level. When we have one side normal substation fed through the transformer, and we have a static frequency converters connected in this tandem, we can eliminate the entire network in between the what is called as a neutral zones. So the entire railway networks to the stretch of say 100-200 kilometer can be considered as a single network. So we don't have to do any kind of disconnection of the internal power network from the catenary to feeding to the railway internal engine. So it can be seamless flow of the current from one section to the other section, and then the entire network can be balanced with the power factor or the reactive power, and then overall efficiency of the network can be increased. So in this sense, by having the static frequency converter working in tandem with the existing or the normal transformer feeding substation, so not only we are balancing the entire network without the neutral zones, but we also balance the entire network in the high voltage side feeding to the entire corridor. So the high voltage network is balanced, catenary side, that is railway network, is balanced in that sense. So the overall efficiency of the power system can be improved to the great extent, reducing of the electrical power, that is maximum demand, to the tune of 20% or more. So the overall tariff you pay to the network provider can be reduced to the great extent. This is all practically proven. So I am not just saying because we have some product. So it is already elsewhere demonstrated that the electrical energy consumption can be reduced to the great extent by approximately 20% or more. So that is what we have simulated here. You can see that catenary voltage is balanced and well within the narrow band of whatever acceptable limits, and then compared to the whatever we have in the standard substation, overall network profile, voltage profile is improved, and your overall network traffic, railway network traffic, can be balanced and increased to the great extent, and we can reduce the headway between two trains, and then overall number of trains running on the corridor can also be increased. So this is by simulation we have proved. Due to time limitation, I will not get into the full details, but what we can see here, suppose we have a 90-kilometer corridor, we envisage around 2 stations with a distance of approximately 60 kilometer feeding on either side, and the distance can be increased to say 150 kilometer, and that means between 100 kilometer we don't need any feeding station. So the overall network voltage profile can be increased. At the same time, the distance is also increased without any neutral section. So the overall efficiency of the traffic movement can be easily 1.5 times or more with the same infrastructure what we have, by just replacing the normal substation with the SFC substation. Similarly, when we have 2 into 25 kV double circuit network, so 110 kilometer corridor can be converted into 230 kilometer corridor without any intermediary stations. So we can have approximately 140 kilometer substations, railway feeding stations apart. So this is how the STATCOM or the load balancer looks like. You can see that there is a transformer to match the network voltage, and then there is a container based STATCOM located inside, and there can be some additional filters due to the harmonics, and then there is a cooling system. So this entire solution can be built in the factory, tested, and then delivered to the site. So within a best possible limited time we can commission and then switch on the substation in a very shortest period of time. And this is a very modular in nature. Suppose you want to add one station now, and after some years you want to add upon another station, it is easily possible to augment it. And the capacity wise, we have rating up to 360 MVR. Maybe 200 to 300 kilometer corridor can be entirely compensated by having one or two load balancer located in one station, or can be in the two ends of the substations. So we can add any number of stations. That is what is indicated here. Say 20 MVA, 40 MVA, 2 stations, and then 80 MVA if you want to have location. So it is a very modular in nature, and it is totally suitable for the outdoor environment. So we don't need much space, and then it can be located anywhere on the entire corridor network, and then feeding to the entire corridor basically. There are some live cases. I will not get into the much details, but this is very interesting application in Australia. We executed this station is called as Ulkuraka. You can go through the internet, Google location, and here we provided 20 MVA static frequency at 50 Hertz, feeding to the single phase 50 Hertz railway grid, and then this not only balanced the entire corridor of approximately 150 kilometer, but also basically compensated for the reactive power, so that the overall voltage profile is improved and the maximum demand is reduced to 20% or even more. This is another largest SFC based railway network in the world. I can say four numbers of 103 megawatt of static frequency converters feeding the entire I don't know exactly the distance, but it is a very big network feeding to the very complex electrical network for the railways. And then all the 4 converters are located in one place, and feeding from the high voltage, converting into the different frequency, like in this case 16.7 Hertz, and then feeding to 25 kV corridor, and then it balanced the entire load on the 3-phase network, and also maintain the reactive power compensation and whatever the power factor for the high voltage network. This is all from my side. I think maybe I exceeded by 5 minutes. So thank you very much for the opportunity, and any questions, I am available. My number and also email ID is available with, and you can always reach out to us. Thank you.